Hello everybody, welcome to your first asynchronous day of the spring semester. We're going to talk about electromagnetic waves today. Now yesterday we talked about waves in general and we learned a few of the characteristics of electromagnetic waves, but today we're going to go into that in greater detail and hopefully come up with an equation that will let us describe a typical electromagnetic wave. Now when I say electromagnetic wave, it's a very fancy word, but we're not talking about esoteric things. We just mean many of the types of waves that you're familiar with, like visible light is an example of an electromagnetic wave, like the light that's being projected onto this screen, or the light that with which you can see me right now, or this little laser right here. Those are examples of visible electromagnetic waves. Of course, we deal with many other types of electromagnetic radiation every day. When you feel something is kind of warm, but you don't actually see any radiation coming from it, that's infrared radiation. We use radio waves all the time in our cell phone communications and what have you. You are going to do a project today where you're going to make a chart showing the electromagnetic spectrum, so we don't need to dwell on that here. Now, when we say that there is an electromagnetic wave moving through a region, the question kind of comes up, well, what's a waving? And as we talked about yesterday, you should have realized that there's no medium required to exist between the source and an observer of an electromagnetic wave, unlike the mechanical waves like sound waves. They require no medium. So the answer to the question of what's waving would be, in classical electromagnetic waves anyway, we're talking about an increase or a decrease in the strength of the electric field at that location, and at the same time, an increase or decrease in the strength of the magnetic field at that location. So we kind of draw that with a picture like this. This little picture is supposed to show that this wave is propagating along the direction of this arrow right here. And you will notice that perpendicular to the arrow, it has little graphs showing increasing sized electric field vectors, and going this way, magnetic field vectors. And then it shows electric field vectors going down this way and magnetic field vectors going into the plane of the board, and then it reverses over and over again. So that's what's waving. It is the strength of the electric field that is changing in its size and also changing in its direction, the fact that it points one way and then points the opposite way and so forth. And as the wave propagates, those changes occur perpendicular to the direction of propagation of the wave. So as we've talked about yesterday, that means that this is a transverse wave. When the change is happening in the perpendicular direction to the direction of travel of the wave, that is a transverse wave. So what we need to do is try to come up with an equation that describes that. Let's just look at the electric field for right now, and then we'll look at the magnetic field. We'll combine them together in a couple of equations here. You can think of the electric field in two different ways as these waves pass by. You can think of it either as watching a wave pass by at a single point and seeing the strength of the electric field get stronger and then weaker and then go in the opposite direction, get stronger and then weaker and so forth. Or you can think of it as just watching the field at one instant in time, measuring its strength at various places at one instant in time. So let's use each one of these ideas to come up with an equation to describe the electric field, and then we'll do the magnetic field after that. So this is a graph of the electric field strength at a particular point in time. So we're going to freeze frame it, we're going to stop the video, and we're going to go measure the electric field strength at that instant at various locations in the region we care about. Now, keep in mind, there's nothing pointing up. There's nothing that moved up this way or moved down this way, okay? All this means is that at that particular point, this point right here, the strength electric field was that much. And at this point, the strength electric field was 0. And at this point, the strength electric field was down that way by that much. Clearly, this is a sine wave, so the function we're going to use to describe this is going to be a sine function. So we can say something like this. We can say the electric field strength is the maximum, which appears to be E naught here. That's what we're going to call the amplitude here for this electric wave. And it's going to have some kind of sine function here. That sine function is going to describe its variation as you go at different locations. So now it just becomes a matter of figuring out what goes in the parentheses for the sine function here. Well, we know we want it to be 0 at position 0, if that's what it's going to be, because that's where the electric field was 0. But we also want it to be 0 over here. And this is what we're going to call one wavelength later. That's what the wavelength is. It's the repeat distance for your wave. It's how far do you have to go on a wave to see it repeating the pattern. That's one wavelength. So if that's a wavelength, then we want the value of sine to be 0 when x equals 1 wavelength. And a good way to do that is to have the value in this parentheses become 2 pi. So we'll say in the parentheses here we're going to put 2 times pi, and we're going to multiply by x, the location, divided by the wavelength. That means that when x is 1 wavelength, you put 1 wavelength in here for x, well, you get 1 wavelength by 1 wavelength, that's 1, so you get the sine of 2 pi. And that's what we want. We want it to be 0 again. But it also works for other locations. How about when x is a half of a wavelength? Well, you put a half a wavelength divided by a wavelength, that's a half. 2 pi times a half is pi, and pi radians, the sine of pi radians is 0 as well. And it works for here. If you put an x is 1/4 of a wavelength, you will get 2 pi times 1/4. That means pi over 2. Indeed, that's the sine of that is 1. So 1 times E naught is E naught. So that is the function we want to have in the sine for the function to give us the electric field strength. How about for the electric field that changes in time at a particular point? Let's say we're going to watch it right here. Let me back this up a little bit and see if I can back it up. Well, can't back it up right now. But if we were watching it over here as this came by, we would feel the electric field strength increase in this direction, then decrease in that direction, and then increase in this direction, and then decrease in this direction, and so forth. So we can make a graph over time that works the same way. Over time, at a particular location, the electric field increases, and then decreases, and then increases, and decreases. So we can represent that the same way. Times the sine of, well, we want to have it be not the wavelength now. We want to have the time it takes for the wave to repeat itself. The time now it takes for the wave to repeat itself. That's one period. So we would say 2 pi times the time divided by the period. And that works all the same reasons that the other thing worked. When t is 1 period, well, 1 period divided by 1 period is 1. So the 1 times 2 pi is 2 pi. Sine of 2 pi is 0. Sine of pi is 0 at half a period. You get the 0 again. The sine of 1/4 of a period, 1/4 of a period put it in there, that's 2 pi divided by 4. That's pi over 2. You get a sine of 1 times E naught gives you E naught. And now we have to combine the two equations together. The way we're going to do it is we're going to put a minus sign in there. And the minus sign kind of makes sense because what it's saying is that if you go out to a further location, what's happening out there is what happened back at the original location at an earlier time, right? As my wave comes by. So right here, let's say it's reaching its peak. And our wave reaches its peak at this location right here, let us say. Let me go ahead and blank this screen out. That's not going to let me do it today. If we watch the wave comes by, at a farther away position, it's going to be what the wave was at an earlier time. But it was an earlier time, it has now shifted over here. And so, we put a negative in there, and that accomplishes that goal for us. That means that you can either go farther in position, but if you go farther in position to see what the wave does, you have to look at what the wave was doing at an earlier time. That's why it's negative. And these two things here, I put in K and omega now. Okay? K is called the wave number. It is kind of like the angular frequency, but for wavelength. It's 2 pi divided by the wavelength. Okay? And omega is the angular frequency. It's 2 pi divided by the period, which, if you remember what you learned about waves, we didn't really get much a chance to do it last year because we were cut short, but the period and the frequency are reciprocals of one another. You should recall that from our study of simple harmonic motion, perhaps. So therefore, 2 pi times the frequency, or 2 pi divided by the period, is omega. 2 pi times lambda is K, the wave number. And with those two things, you have described your electric field. Now, the magnetic field is doing the exact same thing the electric field is, but it's doing it at a right angle to it. So if the electric field is pointing up, the magnetic field is pointing to the right. You get the directions using your right-hand rule. So if I let my electric field be my direction of the my forefinger, and my other fingers are the direction of the magnetic field, my thumb points in the direction that the wave is propagating. Now, there is a relationship between the strength of the E field and the strength of the B field, and it's kind of a surprising one. And it is, in fact, how the nature of these electromagnetic waves was discovered to be just that of light. James Clerk Maxwell took all the equations from electricity and magnetism and brought them together in what are now known as Maxwell's equations. And he realized that the equations predicted a wave of a certain speed should be possible with electricity and magnetism. And what he said was the speed of those waves would be 1 divided by the square root of epsilon naught times mu naught. Now, what I suggest you do right now is pause this video and go look up those values, epsilon naught and mu naught. Put them in this equation, so 1 over the square root of epsilon naught times mu naught, and see what you get. Okay, I'm assuming you all didn't do what I said, but okay, that's okay. No, I assume you did do it. I'm gonna keep a happy thought that you did indeed pause the video. And what you would have found out then that this number is the speed of light. So the speed of the waves that Maxwell predicted would be possible with this electromagnetic equations that he had assembled. He said that they predicted the existence of waves that had a speed of the speed of light. And by that time, they knew approximately how big the speed of light was. And so this was an indication that maybe light was an example of this electromagnetic wave. The first person to measure one of these waves precisely was Heinrich Hertz. So he's given credit for the, he's known by the unit of frequency, which is 1/seconds, was also called a hertz. So in any electromagnetic wave, the strength of the magnetic field times the speed of light is equal to the strength of the electric field. That's in a freely propagating electromagnetic wave. Now, in modern terms, the speed of light is about 3 times 10 to the 8th meters per second, or to say another way, 186,000 miles per second. So that's pretty fast. And the wave speed equation, we can use that equation, the phase equation, to relate the speed of light to the frequency of a given beam of light to its wavelength. Okay? We can say the speed of light is equal to the frequency times the wavelength. So therefore, radio waves, which have a very long wavelength, have a small frequency, small by comparison. X-rays, which have a really high frequency, have a very small wavelength. Let's do a practice right here. What I'd like you to do is write the solution to the wave equation for a plane wave that represents your favorite FM radio station. Now, so what I mean by that is you can say that E is equal to E naught. I'm not going to make you go out and measure the strength of the electric field produced by the radio wave of your favorite radio station nearby. But you should be able to tell me what this is. Sine of kx minus omega t. Okay, so you got to figure out what k is. And k is 2 pi divided by the wavelength. So how are you going to get the wavelength? And our radios are usually written in frequencies. They usually give the frequency of the radio station. There are some places where people actually talk about communications and in terms of the wavelength, like, you know, this many meter band or this many meter band of the radio spectrum. But if you know the frequency times, you know, the wavelength times the frequency should give you the c, the speed of light. And you know that. Since you know c and you know f, you should be able to get lambda. So that's how you're going to get k, 2 pi divided by whatever you come up with for lambda. What about omega? Well, you've already got the frequency now. So omega is equal to 2 pi times the frequency. How do you get the frequency? Well, the numbers they give. Like, I like to listen to 790 when they play the Astros games. 790 is an AM radio station. That's 790 kilohertz. So 790,000 cycles per second. That would be its frequency. On the other hand, if you like to listen to an FM radio station, well, the FM radio band, those are talking about megahertz. So if you listen to 101, that's 101, which is 101.1, I think usually. 101.1 megahertz. That's 101.1 times 10 to the 6th hertz. If you're listening to exclusively to Sirius, well, you can look up just one of the typical. Those are what we call microwave frequencies. They are higher than the radio wave frequencies, and you're going to learn all about that when you make your little diagram today. So do this, look up or just pick some radio station that you can stand and listen to. Write this equation for that. This is for your own edification. If you're not sure how to do it, you can ask me when we have our tutorial time here, and we can talk about it. Otherwise, just know that this is something you're going to have to be able to do if you know the frequency, or the period is usually what you get from a graph. On a graph, to do this, you would look for the wavelength on a strength of field versus position graph, or you would look for the period on the field strength versus time graph, and then you can use those to write the appropriate equation. Now, EM waves, like any other kind of wave, transfer both energy and momentum. The energy carried in an electromagnetic wave is proportional to the square of the maximum of the electric field. So here I have, this is what we call the energy density. I don't know if this is going to be on the AP exam. It might be on the exam that the energy it carries per unit time is proportional to the square of the field strength. So that is the important number to remember from this little formula here. That you take that E naught, the strength of the electric field, and you square it, and that's going to give you how much energy is being transported by that electric wave. Now, I talked a moment ago, I said, I'm not going to make you try to figure out what the intensity of the wave is. That's because as the wave spreads out, the intensity, the maximum of the electric field or the magnetic field, decreases. Because as the wave spread out, it's spread over a larger and larger area. And so if you double the distance that the wave is traveling, well, it's going to decrease in its intensity by a factor of 4. Because as you spread out, it's spreading out to a larger area, and as you know, the area increases by a square of the distance that you've traveled.